Hey everybody, so from last time there was a couple questions from the homework and I want to just talk about it real quick. Took three questions off the homework that all pretty much relate to all your guys' questions and they had to do with like missing heights, okay? So we're trying to find the surface area of this and in order to do that, we're missing one key measurement. So we could easily probably find out the areas of the three rectangles on the outsides of the prism, right? But when it comes to finding the area of the two triangles, the one up here in the front and then the one back here in the back, it becomes problematic because it's not really clear what is the height, the base, that kind of thing, right? And and this would have been nice if this was like a right triangle, but it's not. This right angle is for the box underneath. So how do we get this height? And the answer to the question today is Pythagorean theorem. So if I look at just this triangle, okay, now notice that this is definitely not drawn to scale, and I'll show you why in a second. But we'll see that the base length of this triangle is 40. We know that this length is 36. And this one we are not sure, but because this other side is 36, we are confident that this side also would be 36 because again, if you look straight across, this is rectangular, so this shape, this side would be the same as this side. So this isn't really drawn super to scale because these two sides are equal, but it definitely looks like this side's a little longer in the book problem as well. And I think they did that on purpose just to mess to trick you guys up a little bit. Anyway, if you take a look at this triangle is a isosceles triangle, which means that they're pretty much mirror images of each other. This gave me the idea that if you just slice it right down the middle, that you would be able to set up a Pythagorean theorem problem, because when you slice it down the middle, you would create two right triangles. Now, if you're going to do that, that 40 would have to get split in half. So you would have 36, you would have 20 here on the bottom, and then you could finally figure out what that height is. And once you know what that height is, getting that area of that triangle would be much easier. So just a real quick reminder again, Pythagorean theorem, the legs become the A and the B of the formula. And then the hypotenuse, again, always is the C of the formula. So x squared plus 400 equals 36 squared, which is 1,296. You would subtract 400 from that, and that would give you 896. You could square root both sides, and x would be 29.93. So the height of this triangle, 29.93, could be used then to get the area of this the triangle. So you would use the area equals 1/2 the base times the height. The base would be 40, the height would be 29.93. You could then find the area of this outward facing triangle. You could double that area because there's the triangle there in the back. And then again, there would be the three rectangular sides for the surface area, right? So this 36 by 25 one up here, the 40 by 25 one on the bottom, and then last but not least, this 36 by 25 rectangle here on the side. And if you add up all those areas, you would get the correct answer. Let's continue on. A lot of you guys had questions about heights and stuff for pyramids and cones, so I just wanted to talk about finding missing sides for this. Finding the volume of this would be easy. You'd find the base area, and you would, there would be your height, and then you'd multiply it by 1/3, right? But the surface area of this is a little bit tricky. Now we could get the area of this box here on the bottom. But finding the areas of the triangles, the four triangles that make up the sides of the pyramid would become problematic because this 8 is not the heights of those triangles, it's just the height of the pyramid itself. What we're actually looking for here is really the heights of these triangles, right? So if 10 is the base, if you imagine this triangle tilted towards the apex of this pyramid, we're looking really for that slant height of the pyramid, which would actually be the height of one of the triangles. So if I were to draw this like two-dimensionally, you would have 10, and then we're really looking for this height that's going straight up the middle of it, right? Now, the way we do that is, again, Pythagorean theorem. If you take a look at this right triangle that I kind of drew, this length we actually know because it would be half the length of 12. So really what we're trying to find here is, if you could imagine 8 here, half of 12 is 6. We're trying to find x because that would give us the height of one of those triangles, okay? Same is true, again, if you're trying to find the height of this triangle here for 12. You could, again, do the Pythagorean theorem, but this time it'd be half of 10. Same idea, you could then find the height of the missing triangle there as well. So again, Pythagorean theorem is going to be key to doing that. Last but not least, a lot of you guys had questions about cones and missing heights. You had the slant height, but you're missing the height, or maybe you have the height, but you're missing the slant height. Again, if you think of this like a right triangle problem, you are just, again, doing Pythagorean theorem in order to get the missing thing that you are looking for. Again, this one, it would be set up like this: 5 squared plus x squared equals 13 squared, and then you'd solve for x. So for those of you guys who had questions on that, I just thought I'd do a couple quick ones like that so that you obviously are aware on how to do those ones. Okay, if you still have any questions, please let me know. For today, what we're working on is ratios of similarity. So this is actually a little bit of a review, but what we've been doing over the course of the year is we've been talking about, like, if one shape is similar to another shape, all of its sides would be, similar. They'd be all divisible by the same ratio. We talked about areas being squares of that ratio, and today we're going to talk about volumes and similarity. Okay, so I have 4 similar cubes. Pardon the horrible drawing on this one, but they're all nice cubes: 1 by 1 by 1, a 2 by 2 by 2, a 3 by 3 by 3, and a 4 by 4 by 4. Okay, we're going to find the surface area and the volume of each of these. Okay, so starting with the volume would be 1 by 1 by 1. So the volume of this would actually just be 1. 1 cube would fit into this 1 by 1 cube. Imagine that. Now the surface area would be, there would be 6 faces of this. So there would be 6 1 by 1 rectangles, or squares in this case. The area of one of the squares would be 1, right? And there'd be 6 of those. So 1 times 6, so the surface area would be 6. The volume of this guy would be, let's see here, a 2 by 2 by 2. So that would be 8. The surface area of this would be, there'd be 6 of these 2 by 2 squares. The area of just one of those would be 4. And then again, there are 6 of them. So 4 times 6 would be 24. So the surface area of this guy would be 24. The volume of the 3 by 3 by 3 would be, you guessed it, 27. Because 3 times 3 times 3, so the base area is 3 times 3 times the height of 3. The surface area of this would be, well, there are 6 of these 3 by 3 squares. One of the areas would be 9, so if you multiply those by 6, you would get 54. And then last but not least, the volume of this big guy would be a 4 by 4 by 4, which would be 64 would be the volume of this. And then last but not least, the surface area, if you have a square 4 by 4, that would be 16, and there are 6 of them. So 16 times 6 would be 96. Why am I showing you all this? Well, here's why. If you're comparing the ratios between this shape and this shape, how many times bigger is this shape to this shape? You would say, oh, 2 times bigger. Now, it's great when it comes to lengths, right? So this length was 1, 2 times bigger than 1 is 2, right? This shape would be 3 times bigger than this if these were similar, right? If this length was 1, times it by 3, and now you have all of these 3 by 3 by 3, right? Now, what about the surface areas? Well, if the surface area was 6, we learned a few chapters ago that if we wanted to find out the surface area of this shape, if there, again, if this shape was 2 times bigger, you can't just simply take the surface area or the area and multiply it by 2. 6 times 2 is 12, not 24. So you would have to do something to the ratio to figure out this new surface area. We learned last time that if you're making something, for instance, 2 times bigger, you would have to square this number. In this case, 2 squared is 4. So the area is actually 4 times bigger than the original, okay? So we know that areas, the ratio is actually squared from the original if you think of just the length, right, ratio. We learned that from last time. Volumes is a little different because with volumes you can't, for instance, take 1 times 2, it's not 8, 1 times 4 is not 8, so it's something must be different. So if we are making this 2 times bigger by ratio, 4 times bigger by area, how many times bigger for volume? And if you guessed 8, well, you are correct. But what is 8 in relation back to this idea of 2 times bigger? Well, if 4 is square of 2, 8 would be, anyone, cubed of 2, right? So this would just be 2 to the 1, this would be 2 to the 2, this would be 2 to the third, right? Let's take a look at a shape that's 3 times bigger, right? So the side length for this one is 3 times bigger, right? The area would be square of that. So the area from this shape to this shape would be 9 times bigger because 3 squared is 9. 6 times 9 is 54. The volume to go from 1 to 27 would have to be 27 times bigger. And if you catch my drift, if this one is 4 times bigger than this one, the volume would have to be 64 times bigger than the original one because 4 cubed would be, you guessed it, 64. So notes-wise, this is what I would like you to do in order to be able to do the problems today. Ratios of similarity. First of all, if you have a length or perimeter, because perimeters are lengths too, the ratios can be written like this if you're comparing two shapes, like shape A to shape B. If their ratio is, for instance, 2 to 3, that means the lengths of this one is 2. The lengths of this one would be 3, okay? There's nothing more you have to do to this ratio, and I'll show you what I mean in that for that in a moment. If you are dealing with areas, the area, for instance, is not going to be simply just the ratio itself. It would actually be the square of each of those, and that would be the ratio of the area. So taking this, for instance, 2 to 3 ratio, if we were doing areas for that same ratio, it would be 4 to 9. 2 squared is 4, 3 squared is 9. So that would be the ratio of the areas, again, for this example. And then lastly, volumes. Volumes is cubes of the ratios of the length or perimeter. So A cubed to B cubed. In this case, for this example, each of these numbers cubed, 2 cubed would be 8, and then 3 cubed would be 27. So the ratio of the volumes would be 8 to 27. This can be very useful if you're setting up proportion problems, aka cross-multiplying problems, if you are indeed dealing with similarity problems. So let me show you a few examples of this, and then today you will be practicing a few of these types. So let's try 4 examples. So here we go. If shape A and shape B have a ratio of a similarity of 3 to 2, so shape A 3, shape B is 2. That's their similarity. What is the area of shape B if the area of shape A is 10 square feet? So the first thing I would recommend you do is take the ratio of similarity and take a look at what they want us to do. They want us to convert this into areas, right? So this would just be just the length. If I were to do lengths, I would use this ratio. But because I'm dealing with areas down here, I'm going to convert this to the area ratio, okay? Which would be squaring each of those numbers. So squaring 3 would be 9. Squaring 2 would be 4. This would be the area ratio for this original ratio. What I want you to do next is I want you to set up a cross multiplication problem where this becomes the top of the first fraction. This would become the bottom of the first fraction. So 9 to 4. Which would mean if we're doing shape A and shape B, so A first, then B second, this would be shape A, this would be shape B. right? This is going to come into play when we set up this fraction. I want the A information up top and the B information down the bottom. Now it says, what is the area of B? So I don't know what the area of B is, so I'm going to put an X for B. And then on top, which is the A information, we know that it's 10 square units, so I'm going to put a 10 up here. Now I have a nice cross multiplication problem that would allow me to solve for this problem. So 9 times x, 9x, 4 times 10, 40, and then dividing by 9 on both sides would help me solve for x. So 40 divided by 9 is going to be 4.4 repeating. So 4.4 would be the answer to the area of shape B, okay? That would be it. That's how you do the problem. Let's try another one. Prism A and prism B, so we're talking about three-dimensional shapes, are similar with the ratio similarity of 2 to 5. Now, this isn't saying their volumes similarity. This is just saying that their ratio similarity. So their lengths around the edges from this to this shape is 2 to 5, okay? If the volume of prism A is 35, what is the volume of prism B? So you're dealing with volumes here. So this is the similarity, right? And they want to know a volume, right? So this similarity ratio needs to be turned into a volume similarity ratio. So what we're going to do is take the similarity ratio and this time cube it because we're dealing with volumes. So 2 cubed, 2 times 2 times 2 is 8. And then 5 cubed, 5 times 5 times 5 is going to be 125. So 8 to 125 is going to be the ratio of this situation's volumes, okay? So I'm going to set up my first fraction. And again, because we're dealing with A and B, we'll think of it like A on top, B's on bottom. A on the top would be 8. B's would be 125. That would be the ratio for the volumes. If the volume of prism A is 35, what is the prism B? So again, A on top, B on the bottom. We don't know B, so that's why X is on the bottom. We're going to cross multiply. Equals 35 times 125 would give us 4,375. And then we would divide by 8. And then X would be, let's see here, divided by 8 would be 546.87. So I'm going to round that to 9. That would be the volume of prism B. Let's keep going. Got 2 more here. Shape A is similar to shape B. The area of A is 9, while the area of B is 25. If the perimeter of shape A is 10, what is the perimeter of shape B? Now, this one, we've been going kind of up in ratios of similarity. So we've started with a ratio of similarity and then changed it to the area ratio or the volume ratio. In this case, what they're giving us is the area ratio, right? So the area ratio for this situation is 9 to 25 from A to B. What we want to know is the perimeter of shape B. So we can't use this ratio because perimeters are just, a normal ratio. They aren't squared, they aren't cubed. But unfortunately, this area ratio is not the similarity ratio. So what we need to do is we need to backtrack to what would just be the normal ratio, okay? Just for the lengths. This would be for the areas, but would it be for the lengths? Now, what we've been doing is taking the normal ratio and squaring or cubing to go up, but how would I go backwards? Now, I'm not going to be dividing by 3 or dividing by 2 to go backwards, but if you think of the opposite of squaring something, that would be square rooting. So that would be how I could go backwards. So if I square root both of these, that's how I could go from the area ratio back to the normal ratio. So the square root of 9 would be, you guessed it, 3, and the square root of 25 would be 5. So this would be the ratio for this situation, just for the side lengths. And perimeters have to do with side lengths, so that is the ratio I would need. So I'm going to set this up again. So 3 to 5, so A on top, B on the bottom. We got 3 to 5 equals, and we got, let's see here, the perimeter of shape A. So we know A is 10. We need to figure out B. So we'll put an X there. We're going to cross multiply. 3x, 5 times 10 is 50. 50 divided by 3 is going to become, x is approximately 16.6 repeating, or 16.7 if we round it. Okay, so that would be how I could do a problem like that. And last but not least, we got another three-dimensional situation. Prism A and prism B are similar. The volume of prism A is 8 and the volume of prism B is 64. What is the ratio of similarity between the two prisms? So they want to know just what is just the ratio of similarity between. So what is that normal ratio? Just going, for instance, 8 to 64 is not good enough because that is the ratio of their volumes. We want to know what the ratio of just their lengths are. So the ratio of similarity would just be the lengths ratio. Like before, we square rooted to go from area to the ratio of similarity. What could I maybe do to go from the volume ratio just down to the normal ratio? Square rooting wouldn't cut it. So what would be the opposite of cubing? Now, some of you will have heard of cube rooting. Cube rooting is the same idea of square rooting, except you put a little 3 there to denote the fact of what cubed is that number. So when you cube root something, you're asking the question, what cubed, what times what times what, or what times itself 3 times gives you 8. Now, you probably do this one in your head. That's 2, right? 2 times 2 times 2 is 8. So the cube root of 8 is 2. But if it starts getting a little bit harder, you can do this on a calculator. And the way you normally would do this, for instance, on the ones we were using in class, is you would start by writing what's known as the index. That's the cube root of the problem. And if you look here, with the square root button, which would be second x squared, there's always this type of button, even on like phone calculators with that little x and then the root. If you go second and then that's puts this on the screen, that 3 would be the index of that root, right? And then you would type in the number that you're trying to cube root. So in this case, 64, right? So the cube root of 64 would be 4, okay? So 4 times 4 times 4 is 64. So that's how you would do that on a calculator. So the ratio of this would just be 2 to 4. Now, some of you guys are going to be wondering, well, can I reduce that? Because ratios are technically fractions, right? So you can think of ratios as 2 to 4 or 2 over 4, like we've been doing in the cross multiplying problems. Could you reduce that to, for instance, 1/2 or 1 to 2? And the answer is yes, you could. So this is the last bit of the puzzle for this unit. So the assignment today is going to be more problems like this, so they should be quick moving. If you have any questions about these or if you're stuck, visit office hours from 1 to 2 every day, Monday through Thursday. If not, you guys have a wonderful day. See ya.